Okay, basic number systems. Number system. Can have a base is going to be greater than or equal to 2. You can't have a base 1 or a negative number. Bases have number of symbols equals the base. So if you have base 7, it has 7 symbols. If you have base 16, it has 16 symbols. We're primarily going to be dealing with decimal, base 10, which is what we use every day. Base 2, binary, which is what computers understand. And hexadecimal, a intermediary base that base 16 that makes writing binary easier. So you have, if you have base n, the positions are n to the 0, n to the first, n to the second, third, fourth, etc. And that's going to be the values for those positions. So with base 10, you have the 10 to the 4th, 10 to the 3rd, 10 to the 2nd, 10 to the 10 to the 1st, and 10 to the 0th, or 10,000, 1,000, 100, tens, and ones. Okay? If you're dealing with n equals 2, it's going to be 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, and 2 to the 0th. Or 1s, 2s, 4s, 8s, 16s, okay? And you use these to convert to decimal. So if you have 0, 1, 1, 0, 1, you would multiply 1 times 8, 1 times 4, 0 times 2, and 1 times 1, and 0 times 16. And you'd add them together, and that would equal to 13, base 10. Okay? Now with n equals 16, you have 16 to the 3rd power, 16 to the 2nd power, 16 to the 1st power, 16 to the 0th power. All right. Somebody with a calculator handy, what is 2 to the 6, or 16 to the third power? Like 64, 5, oh, 4096, okay. Can't write. 4096. And 256. And 16. And 1. So you'd have the 4096s, the 256s, the 16s, and the 1s. Okay? So you have, say, A, C, 3, F. You would have, so you'd have 10 times 4096. C is 12. So 12 times 256. 3 times 16. And 15 times 1. See how that conversion is done? The A is 10. B is 11. C is 12. D is 13. E is 14. F is 15. Yes, because there's only 16 symbols, because the number of symbols is equal to the base. So base 16 has 16 symbols, 0 through 9, and then A through F. So let's see here, 4960 plus 12 times 256 is what? 30, 36? No, 30, 72? What's 12 times 256? Somebody with a calculator. 30, huh? 3072? Ooh, that's right. What do you know? So 3072 plus 3 times 16 is 48. That's right. Yeah. I was getting there. And 15 is 15, 14, 18, 19, 1, 0, 1, 4, 4. So this number here in decimal is 44,095. Okay? Now, like I said, the base 16 has 16 symbols, which make the, when you write them out, you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Okay? And those correspond to, of course, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. 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 This type of question will be on the quiz. Not so many digits, though.
How would X and what was going like? How would
Worded? Find the base 10 representation of the following numbers that are in hexadecimal. And then a few numbers to convert. This one, I'm going to show you that in just a second, because a hexadecimal digit corresponds to a nibble in binary. So 0000, 0001, 0010, 0011, 0011, 0100, 101, 0110, 0111, 1000, 001, and 010. See, all the possible combinations of 4 binary digits correspond to the 16 symbols in hexadecimal. So in converting this number here to binary, you would just substitute, let's go ahead and you would just substitute A for 1010, C 1100, 30011. Get that from here. And you put that here. And then F is 1111. You get that from here. So you have a simple substitution. Okay? Likewise, if you have a hexadecimal number, a binary number, you can easily convert it to hexadecimal and use fewer digits. This is a 16-bit number in binary, and it's only 4 digits in hexadecimal. That's why computer scientists like to use hex instead of binary, because it swaps, easily substitutes between binary and hexadecimal, and it takes up less space. And you will find especially when you get into assembly programming, computer scientists are notoriously lazy. Fewer keystrokes, the better. So lots of abbreviations, shortcuts like this to reduce the amount of typing that you need. It comes from back in the early days of computers. Memory was a expensive commodity. So if you have to write something out, type something out, the more you had to type out, the more memory you're going to use up, and space was very limited. Memory has gotten really cheap. Typical laptops nowadays have 1632 gig of RAM, something like that. So that's say 32 billion bytes of random access memory. My first computer that I had in the 80s had 64 kilobytes of RAM, 64,000 bytes. That's it, not much. So you had to be very conservative with your memory usage. And of course, you get terabyte hard drives, which is trillions of bytes nowadays. I think my first hard drive was, first computer with a hard drive, it had 256 meg, I think. Something like that. Or 128 megabytes. Something insanely small. But now converting from hexadecimal to decimal, let's stick with the same thing, same number here. Remember this chart, write it down, and it will be useful on the test and future applications. It will be highly handy until you get it memorized, which is not beyond the realm of possibility. But this is very handy to have. But let's take hexadecimal to binary. So A is, hexadecimal to, we already did to decimal. So let's say we take 3,284 and convert that to hexadecimal. That's base 10. Okay. What power of 16 is that between? What powers of 16 is that number between? The powers were 1, 16, 256, and 4096, right? Right? So 256. It's greater than 256, but less than 4096. So what we'll do is divide this by 256. And what is that? 3284 divided by 256. Huh? 12? Even or? Oh, 12 point something? Okay, so 12. Okay. 12 times 256 is, what is it? Was it 3072? Was that right? Yeah. Okay. So the remainder is 212. Okay. So you have a 12 in the first position. 12 in hexadecimal is C. Okay. Okay, now we take the next position, 16, and divide 212 by 16. That's the 256s. And what's 212 divided by 16? 13 point something. Okay. 13 times 16 is 8. Division. 208? Okay. All right. And then 13 in hexadecimal is D. That's the 16's position. And 212 minus 208 is 4. So that's 4 in the 1's position. And so there is your final result. I'm using bigger numbers than I'm using on the quiz or test or whatever you want to call it. I'm sticking to 16-bit numbers. I mean, I'm sorry, 8-bit numbers. So you won't be dealing with, 3 hexadecimal digits. You'd only be dealing with 2. Okay. So CD4 is equal to base 16 is equal to 3284 in decimal. Okay? Now, where people get tripped up is negative numbers in other bases. All right. Now, the easiest way to deal with negative numbers in binary and hexadecimal is to deal with them in binary first and then convert them to hexadecimal afterwards if necessary. So, say you have negative 72 or 73, negative 73. Okay, base 10. Okay. And you want to convert that to hexadecimal. Okay. First, convert it to binary. 2's complement binary, and this would be an 8-bit number. So to do that, you convert 73 to binary, which is 164 in the 64's position. That'll leave 9, so that's no 0 in the, in the 32's, a 0. 16s would be a 0. 8s would be a 1. 4s, 0. 2s, 0. And a 1's, 1. Did everybody see how I got that? What's the highest power of 2 that is less than 73? 64. And then you subtract 64 from 73. You get 9, which is no 32s, no 16s. There's an 8. Subtract an 8, leave you with 1. So you have 0, 0, 1. Okay, but this is going to be an 8-bit number. This is only 7, so you give it a leading 0 to even it out. Yeah. Please. Oh, to make it an evenly 8-bit number. Yeah. The question will ask for it. And if you're converting to hexadecimal, hexadecimal digits are multiples of 4. So that, it was 7 just straight conversion. Pad it with zeros at the beginning to convert it to make sure it's 8. If you're dealing with 16-bit numbers, you'd pad it with however many zeros you need to make it a 16-bit number. If you need to, yeah, to make it an even multiple of 4. Anytime you're dealing with 8-bit numbers, whether it's negative, positive, or negative. Yeah. If you're doing a negative number, yes, you would be wrong if you did not add the extra bit. Okay? Okay. So this is 73 positive, equals positive 73 in binary. Now, to convert it to a negative number using 2's complement, you flip the bits. Okay? And then you add 1. As 1, 1, 1, 0, 1, 1, 0, 1. And that is equal to negative 73. Flip the bits and add 1. That's all you got to do to make it a negative number. That changes the sign. Now notice, with the added 0 padding at the beginning of the number, a positive number has a leading 0. A negative number has a leading 1. So if it has a 1 and it's a 2's complement number, it has a leading 1, it's a negative number. Okay? And now you just convert it to hexadecimal, which is the simple substitution from the chart that we had before. So 1011 is B, and 0111 is 7. So B7 in base 16 is negative 73 in base 10. No sign, no plus or minus in front of the hexadecimal, because you can't put a negative sign in front of a number in a computer on the hardware level. So it sees that first bit as a 1, and we'll see, oh, that's a negative number. Okay? So to convert a negative number to hexadecimal, you go to binary first, and then convert the binary to a negative number, and then you convert the resulting negative binary number to hexadecimal. Just a few steps, but important to remember them. But yes. Here? No, you add one to convert it to 2's complement, a negative number. You invert the bits. You invert and add 1. Yeah, it just worked out that way. But you invert the bits. And then add the 1 to the inverted bits. Oh, missed one. We'll find later. This is really easy to do it turns out this is really easy to do in hardware. So you can use the same logic gates to add 2 numbers and subtract 2 numbers. So you can easily convert in hardware a negative number to a positive number to a negative number, and then add that to a positive number, and that's the equivalent of subtraction. So adding and subtracting are done with the same hardware in the ALU, or arithmetic logic unit of a computer, just with a couple of little tweaks to it. But that should about wrap things up. So quiz on Wednesday. I had my TA do the answer key to it this morning, and it took him a while, so I'm going to go ahead and give you the full hour for the quiz on Wednesday. So you'll have plenty of time to work on it. I believe it's 8 questions. Some have multiple parts. But yes. And a couple of questions about bases. Yeah. No, it's not multiple choice. None of it's multiple choice. I don't typically do multiple choice. Multiple choice is kind of a challenge to create a quiz, because you have to make not only the right answer, but also plausible wrong answers. So you got to get creative and all that sort of stuff. It's kind of a pain. But anyway, have a good day. See you Wednesday.